Hi grade 11s, good to be back with you. Now today we're going to be looking at a fascinating topic, the topic of capacitors. It links electrostatics and current electricity into one application. Now we unfortunately don't go into all the details, all the uses of capacitors, but it's important for you to understand what capacitors are and how they work to a certain extent. We are going to make sure that you've got all the basics sorted. Although this is a grade 11 topic, it can be examined in grade 12. So make sure you've got the basics all sorted out. Right, let's start by looking at what our focus areas are today. And we're going to say, what are the key concepts? Here they are. We're going to talk about capacitors for a little bit, what they are, take a look at what they look like. The idea of capacitance is an important one as well. So how we measure capacitance, and we'll have some discussion about the charging and discharging of capacitors. Once we've looked at those, we'll then tackle some example questions that are typical of those that you might find in a final exam paper, or just even in your class test. So let's make sure that you've got everything sorted out. Right, let's start with capacitors. So what are these things called capacitors, and what do they do? Well, very simply, a capacitor is a device, it's an electrical device that can store electrical energy. In a circuit, we give it that sort of symbol. Now, that doesn't tell you too much about what's happening there. So what do they actually look like? I've collected some photographs. Let's go and have a look at these and tell you a little bit about them. You'll see they come in all sorts of shapes and sizes. There are different types of capacitors, these flat ones, these rounder ones, and here's another one that you might see if you're doing an electronics project, quite a big one that. It's got two prongs to it, two electrodes to it. There are the electrodes, and inside this capacitor there are some interesting ideas, and I want to just sketch them. If we were to do a cross section of that particular one, this one here, we'd find that it is a spiral of two surfaces. So it spirals around like that, and in between the one surface, I've drawn the one in pink there. Let me choose another color to get the second spiral. And what we would have is a second material that's like that. Between these two, there is a space, and that space is filled with either air or with another substance. The one end of this spiral would be connected to the one terminal, so for example to that terminal there, and the other end would be connected to another terminal, the one at the back there. So the one would be positive and the one would be negative. So let's say that one's positive and that one's negative. And the reason they've coiled them together like that is just to increase the area. So that's the idea. We've got really two plates, two surface areas, one positively charged, one negatively charged, and they're separated by an insulating material. That insulating material is called a dielectric, and we'll have some more to say about the dielectric. Now, a simple model of this, we can simplify this whole picture by actually just saying, well, you know, instead of coiling them up, which is the way they normally are drawn, is let's simplify it by just saying we've got one plate there and another plate there. And this is the simple picture of a capacitor, and you will recognize that we can call this a positive plate, and that means that this one over here is a negative plate connected to the negative terminal of the power supply. So this looks quite familiar. It's about setting up an electric field. And what you should remember from a previous lesson when we did electrostatics is that between parallel plates we have a uniform electric field. So let's go back to the definition of this capacitor. The idea of a capacitor, it creates an electric field, and we are able to hold these charges in position because of the way that the capacitor is formed, the way it's connected in a circuit. And so what we would say, it stores electrical energy because of the electric field. It's important for us to recognize that there's this field between the positive and negative plates. And so all the ideas that we discussed in terms of electric fields and in terms of the forces on charges do play a part in this section of work as well. So how are we going to measure and how are we going to use a capacitor? Well, typically, let's have a look at how we would connect a capacitor into a circuit. And I'm just going to draw a simple circuit diagram, sketch a circuit. The first thing we're going to do is we're going to recognize that we would need a source of energy. We're going to have some cells connected together there, and then what we will have is we will have a resistor, and we will also have a capacitor, and you draw the two lines parallel to each other, something like that. So in this case, what you've got is very simply, you've got a battery of two cells, a resistor R, and a capacitor C. This is known as an RC circuit, and we could even have a switch in the circuit, which is often the case, and we can get more complicated circuits where we have switches and we do different things with them. So this is a direct current circuit, just a single battery, two cells in the battery. Capacitors are also used in alternating circuits. We don't have to deal with that idea in the grade 11 or even in the grade 12 curriculum at the moment. So we're just going to deal with this simple idea of circuits. So what happens when we close the switch is we will try and take the electrical potential energy that's in the battery, and it needs to get the charges in the circuit to move. And so what we find is that there are two processes that involve the capacitors, and we're going to have more to say about them just now. We're going to have a charging process when the switch is closed, and if we were then to open the switch again, we would have a discharging circuit. So there are two possibilities. You can either charge or discharge a capacitor. Now, there are many electronic components around your home even that have capacitors in them. You will see them because what happens is after you've turned off the power supply to, say, for example, an amplifier, you'll see the little LED carries on glowing for a little while. That is the action of the capacitor, which has stored charge while the switch was on, and it's now discharging, showing the light is disappearing slowly. Also in your TV, there are large capacitors. That's why it's never a good idea, unless you're a trained person, a trained electronics or electrician, to even open up the back of a high voltage system like a television or something like a microwave. Very dangerous. There are capacitors. Capacitors store lots of energy, and if you happen to touch a charged capacitor, you're going to cause it to discharge, and that's like setting a lightning bolt going through your body. You don't want to do that. Not a good idea. So let's get to some physics now around capacitors. We want to measure this ability to store energy, this ability to hold charges. It's very similar to a battery in a way, but not quite the same. What do we measure? How are we going to measure? Well, I mentioned the word capacitance. Let's find out what capacitance is all about, and we're going to take a few notes on that. Capacitance is a measure of the ability of a capacitor to store charge. So it's all about its charge carrying or holding capacity. Capacitance, capacity, ability to store charge. The ability to store charge between the plates is measured in the amount of charge per unit of potential difference. So there is the first formula that we're going to find, and you'll find it on the data sheet. Capacitor, capacitance, C is equal to Q, that stands for the charge, divided by the potential difference, the V for potential difference. So if we were to work out the units here, we know the units of charge are in coulombs and potential difference is in volts. So it's going to be coulombs per volt, but we actually give it another name. We call it a farad. Now, farad is honoring Michael Faraday, who obviously did a lot of work on electricity, on electric motors, electromagnetic induction, Faraday's law, but we honor him by giving this symbol for the SI unit for capacitance is known as the farad. Farad is a huge value because it's got coulombs in it. And you remember, coulombs were extremely big. So we got to have some smaller units. And just like we had smaller units for coulombs, we also have smaller units for farads. So we have a microfarad. You remember how we write a microfarad in terms of the SI unit? Well, 1 microfarad, call this 1 microfarad, we would say 1 microfarad would be equal to, micro is 1 times 10 to the minus 6 farads. And in a similar way, 1 nanofarad would be 1 times 10 to the minus 9 farads. And finally, 1 picofarad would equal 1 times 10 to the minus 12 farads. Okay, so having got that idea out of the way, there is something else that I need to introduce you to. We've spoken about the structure of a capacitor. Well, there are some variables there that can change the nature of the ability of the capacitor to hold its charge. The first is the size of the capacitor. Remember I showed you the one that was all spiraled up was to increase the area of the plates. Well, so if we want to recognize that area has got something to do with it, well, here's the formula we're going to be looking at. We can work out capacitance is related to area, but it's also dependent on the distance between the two plates. So here's the formula. We use this strange looking formula. Capacitance is equal to this value here, which is known as the permittivity of free space. And the permittivity of free space is a constant. This is an area value, so it's the area of the plates. And this is the distance between the plates. This is just the distance between the plates. Now, in some times, you're going to also have on formula show a K here, where that K is known as the dielectric constant. Often we don't refer to the K, and we say that we're just dealing with air, and in air the dielectric constant is 1, so it's just the epsilon 0 value that we're looking at there. So this formula we're going to use when we solve problems because it tells us about the structure of the capacitor. Capacitance is related to the area of the plate and the distance between them and the dielectric. And so those are all three very important things. Right, now we must remember that although capacitors are used in many different ways, the definition of a capacitor is something that stores electrical energy. It's a device that stores electrical energy and can be used in many different ways. Different circuits, different applications. But how much energy is there stored in a particular capacitor? Well, there's a formula to work that out. Let's have a look at it. This is an important formula because it's not on the data sheet. So you need to make sure that you take note of this formula. We say the energy stored in a capacitor is U is equal to half QV, or U is equal to half CV squared. Now, you can see how those two are related if you remember that capacitance, C, is equal to Q divided by V, and it's a simple substitution in terms of taking Q is equal to C times V, and if you substitute that one into there, you will get that one. So recognize that this is an important formula to work out in terms of the energy stored in a capacitor, and we're going to do a couple of problems based on that. Now, what about those different ways of connecting a capacitor into a circuit? Like a resistor, which can be connected both in parallel or in series, one after the other in series or next to each other in parallel. Capacitors can also be connected either one after the other or in parallel. There are lots of little investigations you can do, and they're quite fun to see. Just remember this: when you connect a capacitor in parallel, it's increasing the area of the plate. And so what we find is capacitors connected in parallel increase the capacitance because there's an increased area. There's an increased area. So it's opposite to resistors, where resistors, if you connect them in parallel, you decrease the resistance. In similar way, in series, when you connect capacitors in series, what happens is you decrease the capacitance. In series, one capacitor will be, the total capacitance, in series, will be smaller than an individual one. So we decrease because it's decreasing the distance. It's decreasing the distance between the plates when you connect them in, effectively, when you connect them in series. Okay, so what about that idea of charging and discharging? Let's have a few more moments just dealing with that. Remember, that have to be connected into a circuit that has got a resistor, and we're going to have a look at those shortly. So charging a capacitor. Here I have a graph that I want to explain when we talk about charging and discharging of a capacitor. Notice this graph is going to have a potential difference on it. There's the voltage, the red V, that's the P, D, potential difference across a little capacitor. Notice it's not very high, only up from 0 to 3 volts. We've connected this and we've got a data logging output on it. So after a certain time, only 80 seconds, what happens? We start with 0 potential and we've increased the potential difference quite quickly to get to the total potential difference. Now, that's the important part that I want you to have a very clear understanding of, and you need to recognize that in the circuit, the potential difference of the capacitor initially, when the switch was closed, was 0. But when you connect them in to a circuit, what happens is the potential difference increases. So if we had our little circuit again, I just want to illustrate what's happening here. We close the switch, we have a resistor, and we have your capacitor. What's actually going on to cause this? If this was a 3-volt battery to start with, we've closed the switch, there's the switch, it's closed. Now, have a look at what happens. This is really interesting because this battery tries to move the charge around the circuit. We know that conventional current is the movement of positive charge from the positive terminal to the negative terminal. So it's going to move in this way, positive charge, which means that this terminal becomes positively charged. And in that same way, it pulls away positive charge here. And if it pulls away positive charge here, in a sense, it leaves behind extra electrons, negative charges on that terminal. So we've got negative charges over here and positive charges over there. We recognize that this then causes a potential difference. We've got two charges next to each other, they can't join. There's a difference in potential between the potential energy of each of these charges at these places. It builds up. That's why we get this increasing line over here. After a while, they neutralize each other out. We've got the same number of positive and negative charges across the capacitor. On the negative terminal, you've got excess electrons. Excess means extra electrons. And on the positive terminal, we've taken away some electrons. Although I've represented conventional flow in that way, we can think about the movement of electrons as well. So in this sense, we've got a potential difference that's in that circuit. So if we took that charging circuit again, and we looked at it and we said, while it's charging, what do you think's happening to the current? Well, initially, it will be easy for the charges to flow. Let's take an electron. Electron sitting on the battery, it's going to be at the negative terminal, and it will be easy for it to move to the negative plate of the capacitor. Could do the same argument for the positive side. It would be easy for these positive charges, which we're not going to mention exactly what they are. We know the protons and neutrons, the nuclei don't actually move, but the idea of a charge moving does actually happen. So we've got this positive charge moving. What's the flow of current? What's the flow of charge going to be? So what's our current graph going to be? So what you should recognize, initially it's easy. So if we had to draw the same graph, just sketch it for a certain time while it's charging, and we're going to say this is current measured in amps, and we're going to measure time measured in seconds. What's going to happen? Look what's happened to the potential difference. It increased. What do you think happens to the current? Well, it's going to start high initially, wants to move the charges, and it's going to decrease, something like that. And eventually, when the potential difference is no longer changing, we're going to get to a point where it actually gets to zero. So the current is very high at the beginning, so this is high, and it decreases to zero. Over here, it will be zero. Okay, so that's what's happening in the charging circuit. Now, let's look at that circuit, and I want you to think about this for a minute as you examine that idea. Here you've got some very big charge. What's going to happen if I open this circuit and I remove the battery? So I'm going to remove this battery, and I'm going to no longer have a battery there, but I'm going to connect a switch across there. I'm going to connect a connector. So now what's going to happen? This is not the charging circuit anymore. This is the discharging circuit. I want you to think about it, and let's predict what's going to happen. Okay, if you've got a clear idea what's going to happen, well, let's have a look at it. Discharging circuit, discharging of a capacitor. What we're going to say is, well, we know initially that we've got the capacitor, it's fully charged. I'm just redrawing the little diagram because I want to get the picture sorted out. And we said these were all negative charges here. And these were all positive charges. When we charged it, remember now, charge, conventional current, is from positive terminal. So where's the collection of positive charge? Over here. Conventional current is going to tell you from this way around the circuit until all the electrons are neutralized. Or if you think about the electrons moving, electrons are going to move from there all the way around here and neutralize the positives. The conventional current would be that way. So what's going to happen to the conventional current? First thing I want you to notice, it's in the opposite direction. It's not the same direction anymore, it's opposite. When it was charging, it was one way, it's now in the opposite direction. So what's going to happen if I did, first of all, connect an ammeter is I should recognize that I'm going to get something quite interesting happening here. So if I were to draw my current graph again, and I'm just going to sketch it, might as well use that color. When it was charging, my current in amps and time looked something like this. In seconds, I had it decreasing to zero. When it gets to zero now, it could stay at zero for a while. Now when I've closed the switch and I've removed the battery, there's suddenly, at a moment in time, a big negative current, and it decreases. It's not as big as what we started with, but it's going to decrease as the charge gets moved from the plates and it dissipates. So that's the current versus time graph. What do you think happens to the potential difference? Well, remember, let's recall what our potential difference graph looked like. If we take a look from our data, we had a graph that originally increased to a constant potential difference. So it went up and it increased to that. Now what's going to happen? Well, clearly we're going to no longer have as many charges here. If you reduce the number of charges, then you're going to decrease the potential difference. Remember, V is equal to W over Q. So the energy stored per unit charge, or the difference in potential energy per unit charge, you decrease the number of charges you've got, you decrease the potential difference. So what happens when you're discharging is it decreases back to zero, something like that. Now, you're unlikely to have to plot these graphs, but you should know that at maximum potential, when a capacitor is fully charged, it's going to have zero current and maximum potential difference. When it discharges, there's going to be a current in the opposite direction, and it's going to decrease to zero, and the potential difference will also decrease to zero. Okay, so we've dealt with charging and discharging. It's now time to look at some of those exam examples. So let's get straight into it, and let's take a look at question number 1. It says here that we have a 1,5 volt cell. It's connected as shown in the diagram. Whoa, we've got a resistor. Just make sure we've got a pen here. That's your resistor. We've got an ammeter. We've got a capacitor. There's your capacitor, the 2 lines. Notice here is a switch. So there's our switch. And we've got a battery. There's our cell. And it's going to be delivering potential difference. Now, the first question says, will the capacitor charge or discharge according to the setup? So what we've got to look at is which is the viable circuit. And I'm going to start at the positive terminal of the battery. And I'm going to say, look, if I go along here, charges could move to there. And then on the other side, charges could move over there and could move all the way around there. That's a complete circuit. If I have to look at what's happening over here, there's a break in the circuit. So in fact, no charge is going to go up that way. We've got a circuit in which if there is going to be a movement of charge, it's going to be to build up charge on the capacitor. So this must be a charging circuit. So we recognize that it isn't discharging, but it's charging. It's becoming full of charge. It's storing energy. The more charge it's got, the more energy it will have. So now, what do we have to do? Next question. Draw a diagram of the capacitor and indicate the polarity of the charged capacitor and the direction of the electric field. This is a really important question. We need to recognize what's happening inside the capacitor. So what we're going to do is we're going to say, let's get some straight lines, just to draw it a little bit bigger so you can see. And we're going to take it from the diagram, something like that. Now, notice this was the positive charge of the battery. So this is positive. Same terminal is going to produce the same charge. And on this side, you're going to get a negative terminal because that's negative. So when we draw the battery, let's put them in that same order, or draw the capacitor at least. Say that's positive and that's negative. Right. Same number of positive charges as negative charges. 1, 2, 3, 4. 1, 2, 3. I've got one extra, not allowed to happen. So let's just make sure that we can just get the right number. We've got to have 4 so that they're equally matched. Now, what's the electric field going to be? It's an important question. Electric field is what's holding the energy in place. Contained within this electric field We're holding the charges there, and that's producing the potential difference. Because it's between two parallel plates, it shouldn't be too difficult for you to recognize that we have a uniform electric field. So I'm going to draw some parallel lines over here between the plates, and I now need to indicate the direction of the field. Well, the electric field is always from positive to negative, and I indicate it like that. So there's the electric field associated with the capacitor. Let's make sure that we've got the full question sorted out. Draw the diagram of the capacitor and indicate the polarity of the charged capacitor and the direction of the field. We've indicated the polarity. This is positive, that's negative, and we've shown the field. Done it. Not that difficult. I hope you can see that. Right, now let's go to the next question. It says, if the switch is to the top, what happens to the capacitor? So I'm guessing what they're wanting here, might have expressed it slightly differently, saying if instead of the switch closing off that section, let's see if we can close off the other section. So we're going to keep this one open, and we're going to just close off the section between there and there. So we're going to make this open here, and we're just going to have, so there the switch now flicks up to the top, and there's going to be an opening over here, which I can't really indicate because I haven't, well, mind you, I can do it this way. There we go. Use the white pen to scribble in. So the switch is now closed, and there we go. We've got an open circuit here, disconnected the battery. What's going to happen? Remember, this was fully charged, so this was charged. And what happens now when we've got a circuit with a positive charge over here and a negative charge over there? That's potential difference. It's energy, electrical energy that is stored. There's going to be a movement of charge. So what if the switch at the top, what happens to the capacitor? It will discharge. You can't keep the charge there on its own. It's going to discharge. There will be a current in the circuit. Charge will flow, will move. So there will be a reading on the ammeter, and we'll see that. So let's make sure that we've got that sorted out. Remember, in this case, the capacitor now is the source of that charge. It's acting like a battery. It's delivering charge to the circuit. It's delivering potential difference, potential energy at least, to the circuit because there's a potential difference across the terminals. Next question, 1.4. If the capacitor has a capacitance of 450 microfarads, micro, the U, calculate the charge that the capacitor can store. So I think that this is quite straightforward. Let's make sure we've got the formula right. We know that capacitance is equal to charge over potential difference. Let's go back to the diagram to make sure that we've got it sorted out. Remember, we were told initially that we've got a 1,5 volt cell. The charge on the capacitor cannot exceed the charge on the cell. The charge on the capacitor is the same when it's fully charged. If there's no loss of energy, in an ideal situation it would be the same. So what do we want? We want to find the charge. So we want to find Q. We know that we've got 450 microfarads. 450 times 10 to the minus 6 is equal to Q divided by 1,5. So what are we going to do? Let's plug it into the calculator. We're going to see that you get Q is equal to 450 times 10 to the minus 6 times 1,5. Now, please remember, when you're doing exam type questions, even though you can change the subject of the formula, yes, I know you can do it. Don't get stuck on it. I know you can do it. Please don't do that as your first step. substitute the values in, because you get a mark for substituting the values into the correct formula. So you write down the correct formula, substitute into the correct formula, and then change the units over by multiplying both sides by 1,5, and you get Q on the right side. Now we need a calculator, so let's go and pick it up. We're going to say 450, and now we want exponent minus 6 times 1.5. We get the answer, and we'll just need to get that into a more usable value, and we can see that if we convert that to exponential notation, that would be times 10 to the 1, times 10 to the 2, times 10 to the 3. So it is 6,75 times 10 to the minus 4 coulombs. Notice this. This is really important. It was a relatively small potential difference, only 1,5 volts. That's just a little battery. That's just one of those things that you buy in the shops. Not very big, not a massive thing. And we had a very small 450 microfarad capacitor. But look how big the charge is, how many coulombs it is. 6,7 times 10 to the minus 4. Normally, we're talking about micro or nano coulombs. Here we're talking about a much bigger. It's almost 100 times bigger than our normal electrostatics problems. So please take a note of that there is a lot of charge that is released or stored in a capacitor. Right, let's move on. We've done question 1.4. If the capacitor has we've done that one, and we're going to 1.5. So it now tells us, different question, not the same circuit, but it applies a different formula. It says calculate the capacitance, so underline the key words that we're looking for. Capacitance is C, of parallel plate capacitor with plates that measure 3 centimeters by 6 centimeters. The plates are 2 millimeters apart, separated by a vacuum. So we recognize that we don't need to worry too much about any of the dielectrics. We're going to just deal with the straightforward scenario in this case. So what's the formula we're going to use? C is equal to E naught, permittivity of free space. That's going to be in a vacuum. It's always there. We'll look up that value on the data sheet. Then you're going to say it's the area divided by D. Now, to work out the area, we need to change to SI units. And it's really important that you do that change to make sure that you don't make a mess of it. The important thing here is that you've got to make sure that you've got your area right. So we're going to put it in from centimeters to meters. That means we're going from the value of 3 centimeters to meters. 3 centimeters, centi is 3 times 10 to the minus 2 meters. So let's fill in the value. Permittivity of free space from the data sheet, 8,85 times 10 to the minus 12. And then times 3 times 10 to the minus 2 times 6 times 10 to the minus 2. That's your area, divided by your distance, which is 2 times 10 to the minus 3, because it's millimeters. Please notice that. They're sometimes tricky and give you the difference in terms of centimeters and millimeters and so on. So we can now plug that into the calculator. Let's go and do some calculator work, and let's fill it in over here. I want to just clear that value. So the first thing I'm going to do is 8,85 exponent minus 12 times, the first one was 3 exponent minus 2 times 6 exponent minus 2, and we want to divide that all by 2 millimeters, which is divided by 2 exponent minus 3. That's going to give me an answer of 7,965 times 10 to the minus 12. Notice we only do it to 2 decimal places, so 7,97 will be our answer. So when we go back to here, we're going to say it's 7,97 times 10 to the minus 12 farads. Now, can you remember minus 12? What's the shorthand notation for that? What's the smaller unit? Well, it's pico. So we could say, wouldn't leave it in our answer like this, but 7,97 picofarads. Not a very big, it's not a very big capacitor. It's not able to store a whole lot of charge, but enough charge to give you a little bit of a fright. So let's go on and see what we say. Indicate the effect of doubling the distance. Here's an interesting question. What would happen if we double the distance between the plates on the capacitance? So if we looked at this, we recognize, here's the formula. We've got C is equal to a constant, an area, which we're going to say is constant, and we're going to do D, the distance. So I hope you can see that we could replace this by saying C is directly proportional to 1 over D. So what happens if you double the distance? Double the distance, that means you multiply it by 2. Double times 2. So if I substitute into this formula and I say 1 over 2D, and I simplify that, I would say, well, that's equal to a half 1D. Doesn't look a whole lot different. But 1D was directly related to C. So what do I do to the one side of the proportionality, I must do to the other side. So if the effect of doubling the distance, 2D there, was to actually halve the value of 1 over D, then I've actually halved the capacitance. So by doing this sort of calculation, you could therefore say, therefore, C is times a half. It's halved. We doubled the one, we halved the other. It's an inversely proportional relationship. It's not squared, it's just it's inversely proportional. Double the one, you halve the other. You multiply the one by 3, you would multiply the other one by a third. You multiply the one by 4, you multiply the other by a quarter. Other way of saying that, if you multiply the one by 4, you divide the other one by 4. Okay, we've got it. Hope so. What is the effect of using a dielectric between the plates? Now, here's the interesting thing. What's this dielectric we've been talking about? It's the stuff that goes between the plates. It's usually an insulator. And I want to draw a sketch so that you can see exactly what's happening when we do insert a dielectric. We're going to do a question on this a little later, but I want to show you the effect here. So let's erase this. Let's draw the plates in a straight line. I'm going to draw them quite wide apart. Okay, have them like that. And let's have the positive one on this side. Just put 4 positive charges, 4 negative charges, equally balanced. Now, if we put a dielectric, that means it's an insulator, and I'm just going to choose a different color to show this. It could be paper, it could be plastic of some sort. It's an insulator. Means it has the same number of charges, positive charges and negative charges on neutral situation. But when it's put into a field like this, because we know there's a universal field, then what's going to happen is on the insulator, you're going to start to develop little areas of charge. Now notice what will happen. The electrons on this particle here are going to be run away from the electrons there, so this end is going to become slightly positive, and this end is going to become slightly negative. In the same way, the positives over here, the electrons are going to be attracted on this side, and they're going to be repelled on this side. So notice what's happening. We're going to have a polarization within the capacitor. So there's no longer just the capacity to hold on to the number of charges that we had, because we've introduced another charge here. Can you see that? That this charge now cancels out with that charge. It's able to hold that charge, which means that there's kind of room for another one. So another one can come along and take its place because it's accounted for, which means, look, that one's out of the game as well. So another one can come in. So by including a dielectric into a capacitor, what you've got to recognize is you increase the ability of the plates to hold more charge. And so more charge from the battery, if it's charging, can rest on the plate. The potential difference isn't going to change, but the number of charges is. And so the capacitance will increase. So that's the important thing. What is the effect of using a dielectric between the plates? In the question above, we're going to say it will increase the ability of the capacitor to hold charge, which means it will increase capacitance. Good. Right. So there we go. We're done with that one. And I think here's my diagram coming up. It says, draw a diagram showing the electric field between the plates and the field as a result of the dielectric in order to explain the effect of the dielectric on capacitance. So I've drawn you a rough diagram previously of the dielectric and the field and the plates. Now what about the electric field? So we're going to interpret that. Let's interpret it now. We earlier drew the field between the plates. Now we're going to include the field caused by the dielectric. And what we would recognize is we know there's a uniform field. First of all, this one was positive, that was positive, that's positive, and that's negative, and that's negative. It would be an interesting thing to show that initially the field from positive to negative might be represented like that. There's no dielectric in this one. The field lines are relatively far apart from each other, and what we're going to see is that you've got that uniform field between there and there. Now we place the dielectric in its place. Now just go back to the previous diagram, which I drew down here. Notice that's positive, and for the dielectric from positive to negative is in the opposite direction. So over here, what I'm going to do is I'm going to draw in a different field. I'm going to draw in the field of the dielectric. And I'm going to say it's actually weaker, but it's in the opposite direction. The green one. This is the dielectric field. Field due to dielectric. Why have I drawn in the that way around? Because that end was positive and that end was negative. It's because it's being polarized. The material itself has been polarized. And so we can see that that's happened. But wait, what you've got to recognize, because of that ability, this field actually increases because, remember what we said, we are going to be able to carry more charge. So what we should be able to do is to add a few more electric field lines in to show that. So now the field is much stronger than it was before. Let's undo and make sure that that's a white arrow there on the white line. The original field has increased. Why? Because we've been able to increase the number of charges that are sitting on the plates. We've now got 6, 7. 1, 2, 3, 4, 5, 6, 7. So overall, the field is going to be bigger, stronger, but the field due to the dielectric is in the opposite direction. And I think that's really what we're looking at, not so much the increased field, but I wanted you to understand that the field definitely increases as we draw it. Okay. Right, what about our next question? Let's go to it. Question number 2. And here we've got another interesting idea that comes up, and we're going to have a careful look at it. It says calculate the potential difference across a 0,2 microfarad capacitor if it holds a charge of 25 millicoulombs. So which equation are you going to use? Think about it. If you got it, well, what are the options? I think the best option we're going to do is we're going to say C is equal to Q divided by V. Remember what I said before? Make sure you substitute. We know that the capacitance is 0,25 microfarads. Micro times 10 to the minus 6 is equal to, the charge is 25 milli times 10 to the minus 3, and we don't know what the potential difference is. So what are we going to do? We're going to say, well, hold on, that's not too difficult to sort out. V is equal to 25 times 10 to the minus 3 divided by 0,2 times 10 to the minus 6, which equals, let's see what the calculator gives us, 25 exponent minus 3 divided by 0,2 exponent minus 6. And we get 125,000 volts. We write that as 1,25 times 10 to the 5 volts. That's a very big number of volts. You don't want to be holding on to that when it discharges at all. Notice it's not terribly big, 0,2 microfarad, and it's only got 2 millicoulomb. Again, it shows you that this idea of coulombs and farads is an incredibly big number. So let's make sure that we've got that all correct. Now, what about the next question? Here we go. We say calculate the charge carried by a capacitor with a capacitance of 80 microfarads when the potential difference is 6 volts. Notice what we've done here. We've changed it to 80. We've increased that quite a few times, and we've increased the potential well, we've not increased the potential difference, we've changed the potential difference. The potential difference is different. So the capacitance is bigger, the potential difference is nowhere nearly as big. So let's see what the effect of the charge is. We're going to use exactly the same formula, just make sure that we've got all the data written down. Capacitance is equal to, right, charge divided by potential difference. So what was the capacitance? 80 micro, it's times 10 to the minus 6, is equal to the charge. That's what we want to find, Q. What about the V? The V was 6. Not difficult. Substitute it in. Therefore, Q is going to be 80 times 10 to the minus 6 times 6. Take your calculator, depend on it, 80 exponent minus 6 times 6 equals, get it into a usable form, and there we go. It's going to be in your exponential notation, that's 4,8 times 10 to the minus 4. So let's write that down. It's equal to 4,8 times 10 to the minus 4. Coulombs don't forget the unit that we're dealing with charge is coulombs. It's really quite important to stress that. Remember, C on its own stands for capacitance. C with a number is coulombs. The number that goes with the answer to C is going to be in farads, F. So make sure you don't get your units and your unit symbols mixed up. So make sure that you've got all of those sorted out, and we've clarified that. Okay. Next. Here we go. It says, if the capacitor discharges, the current becomes less. Why? So if it's discharging, what's the reason for the current becoming less? So what we need to recognize is the following, that if you've got a capacitance, capacitance is the only thing, the capacitor is the only thing that is giving the potential difference. We recognize that V from Ohm's law is directly proportional to I. So what's happening to the potential difference when it's discharging? Well, discharging means there's a movement of charge, yes, and it means that it's becoming less. The potential difference is less. We showed that on the graphs. So what we recognize, because that's there, potential difference decreases. Potential difference decreases during discharging. And so does, therefore, current. Might start off high, but it's going to decreases in the same proportion. Decreases too. Okay. So it starts off as a big value because the potential difference is high. The resistance of the circuit is constant. Nothing's changing the resistance of the circuit. So we can say V is directly proportional to I. Potential difference decreases, so the current decreases in the same proportion. If the capacitor is discharged, here's one for you to really think about. Capacitor is discharged through a resistor with a high resistance. How will it compare to the discharge through a resistor of lower resistance? Now, this is really quite critical for us to understand. High resistance, low resistance. We recognize it's all related to Ohm's law. Have a look here. We've said if we've got a high resistance, R is equal to V over I. So if we've got a certain potential difference and the resistance is high, then what's going to happen to the current? Current is going to discharge through that resistance. The charges will flow. If it's high, the charge isn't going to move as quickly. The resistor will resist the movement of charge. So charge will take longer. If this was high, take longer. But if you make the resistance low, then what you've got to recognize is you've got the same potential difference, but the current is going to now be able to charge, is not going to be inhibited. It's going to be able to move easier. Move easier, so that means more charge moves. More charge moves. So what does that tell you? If more charge is moving, well, that means the current must increase. Get that? Recognize that there's a relationship between resistance and current, and also between current and charge and time. So if you've got more charge moving, current here is able to move more freely. Recognize that the relationship here between resistance and current is inverse relationship. High resistance, low current, because the charge is going to take longer to move. It's going to battle to get through the resistor. Low resistance, more charge can move, same potential, same energy is pushing the current, pushing the charges. So low resistance, we're going to get high current. Okay. So last question for this one here says, calculate the electrical potential energy of 5 microfarad capacitor if there is a potential difference of 1,5 volts between the plates when the capacitor is fully charged. So what you've got to recognize here is we've got one of these interesting questions about calculating the electrical potential energy. The electrical potential energy was U. Now, let's go and make sure you've got that formula. You mustn't forget it. You must make sure that you've got it. It's not on the data sheet. Remember, U is equal to half, and we've got CV, or we can, sorry, it's CV squared, or it's going to be U is equal to half QV. So you can use either of those two. What have we been given? We've got capacitance and we've got potential difference. So if we look at that, hope you can see that it's not going to be too difficult. We've got capacitance and potential difference. We're going to use this one. We're going to say electrical potential energy stored in the capacitor is 5 micro times 10 to the minus 6 times 1,5 all squared. So get this clear in your heads now. We've got to square that. Don't forget to square it. There are so many formulas that have got squared relationships in them. And the number of learners that make the mistake, they write down the formula correctly, but they don't remember to square. I want to remind you that if you see a square, make sure you square it. So let's do that right here. So here we go. We're going to say it's half 0,5 times 5 exponent. I didn't times. Just clear that. 0.5 times 5 exponent minus 6 times 1,5 volts. And we want to square the 1,5 volts. And we'll say that's equal to that number, which we change to a more reasonable number. And let's see if we can get it into scientific notation. If your calculator comes up like that, and you haven't got it onto the scientific notation, it's not too difficult. Let's make sure that we've got it. We count it. We're going to say that that would be 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. So it's 5,6, 2, and the 2 is going to be changed to a 3 because there's a 5. 5,63 times 10 to the minus 6, and the units here are electrical energy, so it's going to be joules. Okay. Right, here's question number 3. You'll notice the capacitor questions are quite similar. We've seen one like this before, but there is a nice little twist to this one. Let's have a look at it. It says a capacitor consists of 2 plates, each with a length of 5 centimeters and a width of 2 centimeters. The distance between the plates is 2 millimeters. The dielectric is air, so we aren't worried about any dielectrics. Here we're going to recognize that we're asked to say that calculate the capacitance of this capacitor. So the equation we're going to use is E naught, epsilon naught A over D. And in the way that we did the previous one, which was similar to this one, we're going to work out the capacitance by saying we know that value of the permittivity of free space, 8,85 times 10 to the minus 12 times the area. Now, it's 5 centimeters, 5 times 10 to the minus 2 times 2 times 10 to the minus 2, all divided by 2 times 10 to the minus 3. And you're going to get a value when you plug that into the calculator of and I don't want to spend too much time on this. We've done one like it, so I'm not going to worry about doing the calculator. I've done it already. It's 4,43 times 10 to the minus 12 farads. Okay, so just plugging it in, calculating the area. The most important thing in these calculations is to get your units right. So please check them, be very careful, and be familiar with using your calculator in using exponents. So it says here, when fully charged, there is a potential difference of 6 volts between the plates. Calculate the charge on the capacitor. So we know that capacitance is equal to charge divided by potential difference, and we've got the potential difference there. It's 4,43 times 10 to the minus 12, and we know that we're wanting to find the charge because we were told the potential difference was 6 volts. So therefore we can say charge is going to be 6 times 4,43 times 10 to the minus 12. Now, what's interesting is the next question, which says how many excess electrons are held on the negative plate of the capacitor. Now, when you're dealing with capacitors, you've got to remember the stuff that you've dealt with electrostatics. You should remember that the charge on one electron, is the standard charge, or the most simple charge, 1,6 times 10 to the minus 19. So if we now take the value of the charge that we've got there, and if you then have worked that out, that was multiplied through, and let's just do that on the calculator. Clear this one and make sure that we've got it. It was 6 times 4,43 exponent minus 12. And we get this value, 2,658. When you've got all the values in, it was 2,655, but we'll work with this one. That's the charge on the value. And we're now going to take that value and divide it by 1,6 exponent negative 19, and there you go. Notice what you get. 1,66125,000. Now, that's quite amazing that we're getting a whole number, even though we've started with these very big numbers. And that's the beauty of this idea of quantization of charge. We know we've got exactly a certain number of electrons. And although we've displayed it out like that, we can now just show the working. Let me go back and do that working for you. We'll pull it back up on the calculator in a minute. We said that this one was 2. The answer here was 2,6. If we round it off, 6 times 10 to the minus 11. If you keep the correct value on the calculator, we then divide it, and that's what we did. We said we know that's the value of 1 electron on an electron. So the number of electrons is going to be equal to the charge divided by the charge on 1 electron. So that's what we did on our calculator, and we got this enormous number. Look at it, 166,125. 166,125, and then if you take a look, 000. Very impressive that it was actually 000, and there's no fraction in that. and that's a whole number of electrons, because you see, charge is quantized. So there we go. We've got an exact number of electrons, and that was the point of this particular question. Next one. Same capacitor, and it's a bit of a theory question, because we're now asking to apply some things. We've got all these electrons sitting on the negative terminal. Remember, the other thing about that question, it was how many excess electrons are on the negative plate. And we could have asked exactly this opposite question. We could have said, how many electrons are missing off the positive plate? These are extra. These ones, they're not enough. So the same number of electrons that are extra here are missing on there. The charge in each of the plates is exactly the same. So one is positive and the other is negative. So now we need to ask this thing, how can the capacitance of the capacitor be increased? Now, you can't do, we're asking things to make the capacitor different. And there are a couple of things that you can bear in mind here. And the first thing that we've illustrated is you can change the dielectric. So if you change the dielectric and you put a different dielectric in, that dielectric, instead of being air, for example, could be a material such as paper or even a fiber of some sort, an insulated material. It's able to hold on to more charges. So if you change the dielectric, you will increase the capacitance. You could also change the area of the plates. And when I say change the area, you must increase. Remember, if you look at the formula, you will see that capacitance is directly proportional to area. So if you double the area, you'll double the capacitance. And remember as well that we had the formula C is equal to epsilon naught K A over D. Now, if you got a dielectric with a higher K value than 1, which is the value for air, then that's going to change the total value there. So if this one goes up, that's what we're saying. If we increase that one, you're going to increase that one. Well, look at that again, and you begin to see, but hold on, what about doing something there? If we did something like decreased the distance, so if we decreased, brought the plates closer together, decrease the distance between the plates, then you're automatically going to increase the capacitance, because what we know is C is directly proportional to 1 over D. So if you halve the distance, you're going to double the capacitance. If you quarter the distance, you're going to multiply the capacitance by 4 times. And there's the last question. Now, these are very popular questions. They can even come in the multiple choice section of your final matric exam, where they're asking you to manipulate variables. And we've got to look at 2 variables here. And it's interesting that we've got something that we need to just have a careful look at. The charge on the capacitor is doubled, and the distance between the plates is halved. So we've got 2 things. We've got charge changing and distance changing. By what factor will the capacitance be changed? Show by means of mathematical relationships the reason for your answer. Well, we can't just guess now, so we've got to be very careful. What are the relationships? Well, we know that C is equal to Q over V. And if the potential difference is constant, then that means that we can say that C is directly proportional to Q, which means that if you, what's the change you're suggesting? The charge on the capacitor is doubled. So if we do, this is how I like to do it. I like to say C old, the capacitor old, is equal to, let's just say, a constant times Q. And we just don't worry about the constant at the moment. And now what's going to be the new C? We say new is going to be K. The constant's not going to change. The potential difference is not going to change. The new Q is 2Q. Okay? And now we substitute in and we expand and we say, wow, we can just rearrange that and that becomes 2Q. 2K times Q. But look what 2K, what was KQ? KQ was the old C. So the new C has to be 2 times the old value. So it's 2 times what you had at the beginning. Okay. So we know that by doubling the charge, you double the capacitance. So double the charge, you double the capacitance. That wasn't the only change that took place. What was the other one? The other one was that we halved the distance. So I'm going to write the formula here for that equation, second formula, which we know is going to be the epsilon naught, the area over d, and that's all a constant. So I'm going to write it in this way to say, well, we know that means that capacitance is directly proportional to 1 over d, or another way of saying that is saying the capacitance, the old capacitance, can be written as K, a constant, another constant, perhaps just change the writing of that. Let me just, different constant. I don't want you to think it's the same K. K times, or times 1 over d. Okay, so that's the old value. Well, what's the new one going to be? C, the new capacitance, is still going to be K, but what have we done to the d? We've halved it. So in the brackets here, I'm going to put half d, half what the original d was. Now there's a bit of arithmetic, and I'm going to say K is still there, 1 is still there, half is on the outside, d is over there. What do you do when you've got a fraction and you're dividing by a fraction? You invert and you multiply. So that half becomes a 2. So we get 2, and look here, 2k 1 over d. So we've just treated that on its own. But what was this expression here? Look, what have we got? K 1 over d. We've tried to manipulate it so it looks like that. And we can quite justifiably now say that that is 2 times the old capacitance. And so what does that mean? It means that when you half the distance, you double capacitance. Now what happens if you do both? Double the charge and you half the distance. Well, this was a factor of changing the capacitance by times 2, and this is a factor of times 2. And if you do times 2 times 2, then overall, the overall effect is 4 times. So by halving the distance and doubling the charge, you have increased the capacitance 4 times. Please make sure you go over those relationships. There are a limited number of relationships, directly proportional, inversely proportional, really very important. We've done some of them when we did kinetic theory. It's really important that you do them in every section and understand the variables in each of the experiments. Well, I hope you've had fun learning more about capacitance and revising some exam questions. I wish you well when you tackle the questions on your own. Don't forget to do the exercises. They will help you to reinforce your learning from today. Until next time, bye from me.